Welcome to this lecture on cardiac output, where we examine more closely the thermal dilution technique. In this lesson, we'll have a look at the theory behind the Fick principle and its application to the thermal dilution equation, the Stewart-Hamilton formula, that is used to generate an electronic temperature washout curve that provides us with a thermal dilution cardiac output. This is John Boland. You may as well know in advance that there are several options for determination of cardiac output. I say determination instead of measurement because they're not measurements. They're derivations or determinations, not a direct measured value. There are two basic types. There's the invasive methodologies and non-invasive methodologies. Of the invasive, the Fick method has always been the most accurate and probably respected and accurate method. There are two methods, direct or indirect, and we'll look at those in another lecture. But in this lecture, we're focusing on thermal dilution, which used to be called dye dilution before technology advanced. There's other forms of thermal dilution, such as energy pulse thermal dilution. There's also a pulse pressure contour analysis, and of course, your echo determinations of cardiac output. The non-invasive technologies involve Doppler echocardiography, cardiac output partial rebreathing technique, inert gas rebreathing, and impedance cardiography. There are many of these systems in use worldwide. In our hospital, we've used most of these at some time or another, and worldwide, thermal dilution still dominates the equation. In time, we'll have a look at what all these mean, but for the moment, let's have a look at the Fick equation and theory, and then we'll have a look at how the thermal dilution method works. The Fick principle. In simple terms, if an indicator substance enters a flowing stream, as shown by this substance entering a tube, a flowing tube, its concentration at a point downstream is proportional to its concentration before its point of entry and the flow of the stream. That is almost intuitive, but this principle permits calculation of flow once it's applied as a mathematical formula. And in fact, flow equals the amount of indicator entering the stream divided by the difference in concentration of indicator before and after the point of entry. That's it. There are only three variables in the equation, and the fourth variable is cardiac output. We'll have a look at the formula in more detail when we discuss the Fick method, but I mention this because the Fick principle is used in the calculation of the Stewart-Hamilton equation, which is used to calculate thermal dilution cardiac outputs. Both dye dilution and thermal dilution techniques are therefore based on the Fick principle. Dye dilution was originally used. As technology advanced, it was discontinued. I've never seen it used. By the time I started my career, thermal dilution was well and truly entrenched, although it would not make a footprint in my hospital until a number of years after I started. We stuck to the direct Fick method and eventually converted to the indirect Fick and eventually converted to thermal dilution. Have a look at this drawing. A cardiac output measurement by indicator dilution, think thermal dilution as well, has three principal states. Shown here, 1, 2, 3. An indicator is brought into the circulation, so you have to inject the indicator. It's called the injectate. The indicator has to mix evenly with the bloodstream. The second stage is mixing, and of course, the indicator is diluted by the bigger volume of blood. And then the concentration of the indicator is determined downstream. So it has to be detected. It has to be injected, it has to be evenly mixed, and it has to be detected and quantified. Let's go back for a quick little bit of history. Early thermal dilution. In 1897, a man called Stewart injected a bolus of sodium chloride into the central venous circulation of anesthetized dogs and rabbits, and then collected blood samples containing diluted sodium chloride from a femoral artery catheter. An electric transducer on the contralateral femoral artery sensed the arrival of the diluted injectate. So a little light flashed, and Stewart knew when to collect the blood for analysis. And by doing this, he developed this concentration time curve that became known as the Stewart-Hamilton formula, time concentration curve. You can see this is a graph. You can see this is a graph, in this case, of the change in concentration with time as the injectate is absorbed into the blood and then dissipated. He worked out a formula where flow equals C, the concentration of the dye, and the volume of the dye at time 0, the point when it was ejected, divided by the integral of Ct dt. And you all know that the integral of an equation generates a value equivalent to the area under that curve. And because that area under the curve is in the denominator, the flow is indirectly proportional to the area of the dilution curve, meaning is proportional to 1 over that area. In short, cardiac output is a simple formula that equals, in simple terms, the amount of injected indicator over the area of the dilution curve. Obviously, the mathematics are a little more complex, and we will never have to work out the formula from first principles or even apply it at all. It's all done electronically. The original technique used indocyanine green as an indicator, and continuous withdrawal of blood into a sensing cuvette was the conventional method used to measure cardiac output in patients until the 1970s. We no longer use dye, we use temperature with advances in technology. And we just quickly read this, another bit of history. It's worth reading. The thermal dilution technique uses a special thermistor tip catheter, a Swan-Ganz catheter, that is inserted from a peripheral vein into the pulmonary artery. A cold saline solution of known temperature and volume is injected into the right atrium from a proximal catheter port. The injectate mixes with the blood as it passes through the ventricle and into the pulmonary artery, thus cooling the blood, if only slightly. The blood temperature is measured by a thermistor at the catheter tip that lies within the pulmonary artery, and a computer is used to acquire the thermodilution profile, meaning that temperature time curve. The computer quantifies the change in blood temperature as it flows over the thermistor surface in almost the same way as that dye concentration time curve of the original Stewart equation. The cardiac computer then calculates flow and, of course, is calculating cardiac output from the right ventricle using blood temperature information and the temperature and volume of the injectate. These are the only 3 variables. The injection is normally repeated a few times and the cardiac output is averaged. Because cardiac output changes with respiration, it is important to inject the saline at a consistent time point during the respiratory cycle. In normal practice, this is done at the end of expiration. In practice, we can't accurately time the injection without use of a computer to coincide with the same phase of the respiratory cycle with every heartbeat. But I have noticed that operators do watch the respiratory cycle of a patient when they do the thermal dilution injections and try to time it at a consistent point in the respiratory cycle. It minimizes, if only a little, another potential source of error. Let's have a look at this slide showing the thermal dilution technique. The thermistor detects the change in temperature of blood as that bolus of cool saline courses through to the pulmonary artery. And it uses that change in temperature over a fixed time period to derive a cardiac output from the speed and degree of temperature change. And the indicator in this case is temperature. And this is the thermal dilution curve that it generates and gives us a number. And the thermal dilution technique is as simple as that. That's why it's favored by so many. Let's have a closer look at this curve. Again, the Swan-Ganz catheter in the pulmonary artery, and a graph showing that temperature curve, temperature time curve. This is the onset of the cooling. It reaches a peak, as you can understand, and then it starts to gradually warm up again so that it goes back to its starting temperature. Let's read this. The introduction of the cold injectate causes a reasonably rapid upslope to a peak, a gradual downslope, and an exponential decay of that thermal signal. The cardiac output computer begins integration of the area under the thermal dilution curve until the exponential decay reaches about 30%. Beyond that, it becomes unreliable and extrapolates the exponential decay to the baseline. It needs that full curve in order to calculate its equation. And it cuts off this point because if any of the indicator, whether it's dye or temperature, recirculates, then it will have an effect on that generation of that curve. It's called artifact due to recirculation of the indicator. That's just standard. That's a magnified image of that curve. I thought you might like to have a closer look at it. You can see the writing a bit clearer. My screen is always a bit small when recording. It's a decreasing temperature on that axis, and the baseline is time. The text is the same as in the previous slide. Now, I chose this slide to answer the question, how can we use cardiac output in the pulmonary artery to determine flow in the left ventricle, which is what cardiac output by definition always has been, stroke volume times heart rate. And that is because blood flow is linear through the circulation. On average, pulmonary flow at this point is the same as systemic flow, arterial flow, at this point, beyond the ventricle in the aorta that isn't shown. And that is because blood flow follows a linear trajectory, as shown here. The right atrium is in linear continuity with the right ventricle, right atrium, right ventricle, the pulmonary blood vascular system, left atrium, and the left ventricle, and the aorta. Not in series. And that's what makes it possible. On average, not for every single beat, the blood through the pulmonary artery, the flow of blood through the pulmonary artery will equal the flow of blood through the aorta. Now, we average several beats to calculate cardiac output. Measurements can vary by up to 10%, and we use only values that lie within 10% of the mean. We don't just average several beats, we average several calculated values of thermal dilution cardiac outputs. There are a few potential modifications that can be made and have been made to the standard thermal dilution technique. One is a transpulmonary indicator dilution technique. With technology again, they decided it's a little tedious. It can be tedious to keep advancing the Swan-Ganz catheter into the pulmonary artery to record cardiac output. So they developed technology to analyze cardiac output simply by injecting a bolus of indicator into the central venous system from a peripheral vein. And our systems are now sensitive enough to detect a temperature change, not between just the right atrium and the pulmonary artery, but between a more proximal site in the venous system and the aorta. So this is very useful for patients in ITU, where you can have patients with tubes and catheters in multiple orifices and blood vessels, and they need to do repeated cardiac output evaluations. This slide shows pulmonary and transpulmonary thermal dilution curves after injection of cold saline into the SVC. So instead of having to do a Swan-Ganz catheter into the pulmonary artery, now, as shown by this P curve, the injectate is done into the femoral vein or a peripheral vein, and the temperature change is detected late in the piece by the time it reaches that aortic site. And it reaches a peak, and it then calculates a normal thermal dilution curve. The pulmonary artery thermal dilution curve appears earlier and has a higher peak temperature than the femoral artery thermal dilution curve. Thereafter, both curves soon reapproximate baseline. So technically, the catheter doesn't have to be in the aorta. It only needs to be in the femoral artery and the femoral vein. A great advantage. The advantages of pulmonary thermal dilution. Thermal dilution is now considered the standard method for cardiac output measurement. Some even call it the gold standard, but the gold standard is still thick, except that nobody seems to use it anymore, or very few. There is good correlation with earlier methods. It's a simple measurement technique. Repeated measurements are possible. Pulmonary artery catheterization may provide a calibrated constant cardiac output, meaning continuous repetitive measurements, and it provides pulmonary artery pressures, pulmonary artery occlusion pressures, meaning wedge pressures, mixed venous saturations by allowing collection of blood, and optionally, right ventricular ejection fraction and right ventricular end diastolic volumes. These are all what we call derived hemodynamic variables. And we'll have a look at many of these again later in our lives. There are limitations, as there are to everything with thermal dilution. There is a limitation to the reproducibility of the measurements. There are limits on the frequency and number of measurements. You can't keep injecting 10 mils of dye into a patient in great quantities. There are complications that can be associated with delivery and placement of a pulmonary catheter, such as infection, perforation of a vessel, and a pulmonary artery catheter-based cardiac output may not be clinically useful during periods of hemodynamic instability, as it is averaged with time delay, not a real-time instantaneous delivery system. Apart from that, in spite of these limitations, it's a very popular and extensively used system worldwide. And with that, I'll end this lecture.